great, OBS. Let's try again. Maybe I'll try to be more engaging this time. Like I'm actually having a conversation. I focused on GR as an important example of geometry in physics because unfortunately in mechanics, geometry is fairly limited when you're just discussing the shape of trajectories in physical space. You have ordinary differential equations depending on time. The trajectory evolves according to the kinetic energy, the mass, inertia, and the forces applied to a particle. But in space-time, you're allowed to discuss fields. And these fields can be used to shape the trajectories of particles, but they can also evolve on their own and interact with each other. And these fields are spatially extended objects. They exist over volumes or four-dimensional hypervolumes in space-time. But in either case, both particles and fields are described locally in terms of the same kinds of quantities, either scalars, representing mass, charge, density, or directions, described by vectors and higher order objects called tensors. And I focused on the particular case of how if you I drew a green geometric arrow on a tangent space at a point in space-time or in a two-dimensional space. I drew a picture of a surface because it's rather hard to draw 4 dimensions. How do the component projections of this green arrow onto a given frame or basis, E1 and E2, or in space-time, E0 through E3, how do those components differ when you pick different frames? And the notation I'm using, E1, E2 is one starting frame, F1, F2 is another frame. And you can relate the components of the green object by just knowing the components in one of the frames. I should be using black. And the law to transform the frames will give you a law to transform the components, but it differs from the transformation of the frames itself. And that sounds counterintuitive, but if you just add the requirement that the overall geometric object, in this case the green arrow, has to remain the same after the transformation of frames, think of frames as a measuring device, then you will get the transformation law of the components. So I showed here the transformation between two frames is described by a matrix because each vector in the frame of the resulting basis has a combination or lists of projection values onto each of the initial basis vectors. And this is for each of the f's and for each of the e's. And so those pairs of possible values of projections, you can project f1 onto e1 or e2 or f2 onto e1 or e2. That gives you 4 projections in this two-dimensional case. Gives you a matrix. And I compact it into this equation where I say bracket around A represents the matrix of A, acts on the frame of E, and gives you F. And if you compute A's inverse, and A's inverse exists for the geometric reasons that the F vectors are independent of each other and the E vectors are independent of each other. Preserving this independence implies an invertible matrix. Maybe I'll explain it properly in another step. But you apply this inverse to F and you can get E back. And this inverse has well-defined numerical components, just like A does. So now we calculate over here what exactly are the transformation laws relating the components of X in the E basis to the components of X in the F basis if we know A takes the E basis to the F basis. Well, the result was, if you imagine that these components do exist and you call them X prime 0, 1, 2, and 3, now we're working in a 4-dimensional space-time because it's the interesting case and it's not different in any other dimension other than making these numerical indices, subscripts and superscripts, range through more values. Then each of the F's expands into a sum of the E's, maybe I'll circle that. For example, F0 has this expansion into the E's, and so the lower index of the A represents which F you're producing, and the upper index represents which E you're acting on. So if we expand each of the F's in this X prime sum, we can collect just the E0 parts and regroup them together, and just the E1 parts and E2 parts and so on. Imagine you're circling this way. Instead of each X prime component is associated to a row, because it's associated to an individual Fi, well, you get this for E0. And because these are all scaling the same E0 in the same direction, you can imagine that the overall result is just the sum. But because we have an expansion now in terms of the E0s, it should be the same as the original expansion, where the components were just X instead of X prime. So we did E0. In this case, the E0 component can be expressed either just as X0 or the sum combining the A matrix components and the X prime components. But because the matrix acts on X prime and not on X, it acts in the reverse direction of that it acts on the frames, where A takes the E frame to the F frame, but it takes the components in the F frame to the components in the E frame. So it's in the reverse direction. And of course, I said that A has an inverse, which acts in this direction. So if we want to describe, if we're given a description of a geometric object X, and now I'll write a summation notation. So we use Greek indices for space-time because we wanted to separate Latin indices to refer to the purely spatial dimensions 1, 2, and 3. Mu ranges 0 through 3 for space-time dimensions, and the X mu's are these numerical components. The E mu's are these geometric basis directions, this frame. And one can re-derive everything we did so far in the summation notation, but it's more compact, and maybe for the first time it's a little more clarifying to see it all written out like this. That X's description in the case of E is just given by the E frame and the X mu components. So we can't exactly just take the matrix A and get what we want, because even though A takes us to the new frame, F, we need to also calculate A's inverse. I'll write E to show that I'm using the E components. And the prime, I'll keep the prime. And this makes a little more sense if you look at how X is a combination of X mu and E mu again. Because if you transform each part individually and then sum them, we have the result of the transformation being A inverse X mu E, and A, you might have a guess as to what will happen here. We're going to combine these somehow in a sum, but we should write out the notation properly. So if I'll just fix a notation for the inverse first. So I will call the components of A inverse B, and I'll use the same notation convention that I did for A. So now this is going to be a matrix acting on these components. This is a matrix acting on these vectors. Each of those involves a sum. So the first sum will be B mu, and we need another Greek letter. is common. That's what I'll use, x mu. And then we need another sum of the A's acting on the E frame. So the E frame will have a mu here. And let's see. We need another component. I think it would be wise to not use mu for E because there's going to be some overlap. So how about we use alpha? Alpha is a little too close to A. Use beta. And then I'll also use nu for a reason, well, you will see in a moment. So we remember before that these are just the x primes. And since we're summing over mu, and mu disappears, the result only depends on the index nu. And this is in the F frame for a given value of nu between 0 and 3. And then this, again, is just F nu. And if we sum over nu, we get x again. So each of these decompositions makes sense. You can think of it going in reverse. F decomposes into the E's. X prime decomposes into the X's with the B. But you might also see that the indices of the matrices B and A line up on the nu. So there's nothing stopping us, and this really should also be a sum over nu. That's where that comes from. It's a sum over two inner sums. And maybe there's a three-dimensional picture. We have three sums, but you can work out the algebra. You don't need to draw a cube of terms to see this result. But because these indices line up, you can just rearrange the sum so that you sum over the nu's first. So you move this summation inside, symbolically. Let's try that. Since the x mu's and the e betas don't use the nu index at all, it's the one that looks like a v, well then we're just refactoring scalar components of the matrices, so there's nothing that stops us from doing this. B mu nu A nu beta. And then this result leaves out the x's, since they don't, it doesn't need to be in the inner sum, which only depends on nu, and the e betas, and we still have to keep these other sums over mu and beta, but we'll see that this simplifies a lot in the end. Well, B was just the inverse of A. So what is the matrix acting on the inverse? It's just the identity with ones on the diagonal and zeros otherwise. And there's a notation for this. So keeping in line with our indices, mu beta, we just have 1 0 0 0 1 0 0 0 0 1 0 0 0 0 1. And beta goes this way, and mu goes this way. Well, let's write that inner sum. We'll just say that the result is this delta. And it's mu on the bottom and beta on the top. Well, this inner sum disappears, but we still have our two outer sums over mu and beta. And we could rearrange these in either order, but in this case, since we have the mu on the inside, you can imagine what would happen when delta acts on x. Well, if mu equals 0, you have I'll write on the left. X mu, mu is taking values now. Delta beta, delta 0 beta, no, that's not right either. Delta 1 beta x1, delta 2 beta x2. And you can maybe see the pattern. For some value of beta, so if beta is 0, the only delta component that is not 0 is the one that matches the component mu. Another way of saying this is that for a given value of beta, the result of this is always x beta. We can dwell on that for a second. We have to have a resulting sum over beta to scale the e betas. We're summing over mu, so the mu index is gone. And so for each e beta, what is the scalar factor in front of it? So in that way, it's easier to think about it as taking the outer sum first. You pick a value of beta, and then the value of mu has to conform to the value of beta. So we just get, which is the original definition of x. And somewhere in here you can connect these two equalities and see that x has this expression in either basis. So the fact that the components transform inversely to the frame is just a result of the frame transforming a certain way and having to adjust the components so that the overall object remains the same. Now, it's harder to explain the geometrical meaning of tensors. They're not exactly arrows with directions that are tangent to some object in your manifold, but algebraically they're quite similar. Where at each point in spacetime, if we pick a type of tensor, and a type is described by two numbers p and q, a vector is just a type 1, 0 tensor, and a covector is something called a type 0, 1, where each covector has a projection onto a covector basis, similar to a vector basis of tangent vectors, and all we use to describe it is that in a given frame E, there is a dual frame. These covectors can be interpreted as linear functions on the E. So if I take E mu and I act epsilon mu and I act on E beta, again this delta symbol comes up again, but now it has a different meaning. The result is only a 1 if mu equals beta, and 0 if mu is not equal to beta. The way you can think of these is if we have an E frame, then a particular epsilon is a field of values on this tangent space, but the field varies linearly. So the field epsilon 0 aligned with E0 has level sets which are lines, and notice that there is a middle line along the E2 axis where epsilon 1 equals 0. And because epsilon 1 acting on E2 has to be 0. And red denotes an increasing value, blue denotes a decreasing value. And the value 1 just happens to take place at the tip of E1 and along that entire line. And that's how you can picture this dual basis of what it represents geometrically. But algebraically, it's just another collection of symbols, and you can determine them by this rule. Now you see that they take scalar values on the E basis. They behave a lot like components of a vector. So if an E basis frame transforms under a matrix A, and a dual frame must transform under the inverse, well, then we can also look at components. We have, and this is where the convention for the upper and lower indices comes from. X has components in E, and we need dual vector components, which aren't necessarily corresponding to our vector, because dual vectors and vectors live in different spaces. We'll say y lower mu transforms by A. But the overall pattern is the same. The pairing of dual components with dual vectors and the pairing of components with vectors transform oppositely to preserve an overall geometrical object, whether that is a covector or a vector. So then this PQ tensor represents some product combination of components of vectors and covectors. So if we have a covector y, keeping in with our previous notation, and we want to take a type 1,1 tensor, we take a covector and a vector, we want its components to look like products of components of these individual objects. And we want them to range independently of each other. Think of it like a two-dimensional array. So we should pick different indices. We can say y lower beta, x upper mu are the components of this object. And just for formal algebraic reasons, we need a notation for what geometrical thing this is scaling. And that geometrical thing is a combination of the epsilon and E basis. Epsilon index has to match the Y index, and the E index has to match the X index, but on the opposite. And that would be a 1,1 tensor in space-time, where the components beta and mu range from 0 to 3. There might be some confusion as to the geometric meaning of this thing, but all it really says is that the dual vectors can transform, the vectors can transform by opposite matrices, and then corresponding matrices apply to their components. And we can still play the same game with the sum so that the overall result is the same. The overall result is t. We still haven't really understood what it is geometrically. But if we just have the rule that, for example, I took E0 plus E1, epsilon 0 plus epsilon 1, and this product is called the tensor product, applied to, let's say, E3, it distributes over sums of vectors on either side. One way to think of it is as a version of polynomial multiplication for vectors. So multivariable polynomials can have different variables x and y and z. And multiplication of polynomials symbolically is like this kind of multiplication of vectors and covectors, where you just produce new monomials that are different from the old ones. And the mathematical term is freely. So the tensor product freely produces new vector space elements out of old ones that can't be described by projecting onto the old ones, meaning as components. They just exist in new directions. So all it really means to have a tensor of type PQ is that it has components, and we picked the convention that the first index in P was a vector part. So that would be, and we'll try to be as consistent as we can. We picked mu for vector components. So we'll do mu1, mu p, and beta 1, beta q. And we have a big product here. E mu1 tensor E mu p tensor epsilon, and the index is up again, beta 1. And now we're in a position to really explain why we have upper and lower indices. It's really just because if the lower index objects, in this case the geometric vectors E, each transform by matrix A, then so do the covector components, because the indices are both lower. And the upper index pieces transform by A inverse, except the indices of A, in this case, because we have a product of geometrical objects, all have to be independent. So there'll be many copies of the matrix A appearing in the transformation law. If we have F, what's a Greek letter close to F? I guess we can just use F again, but we'll know what we're talking about now if we have F lower indices and F upper indices, right? But we'll say prime to show that these indices are different, because there'll be a copy of A taking E mu1 to F mu1 prime, where we have an A has to have opposite indices now. Upper mu1, lower mu1 prime. And so the indices match the vectors they transform on. And this matching of indices for our overall tensor T of type PQ will have the same kind of cancellation, where you can either sum over the bases or sum over the matrices A themselves and combine them with their inverses. Since for every matrix A acting on these, there'll be the same number acting on the upper indices, but with inverses, so there'll be B matrices, and those can pair up and cancel, or we can rewrite in the new basis and just have new components. In either case, we have a description of these general objects, T, with type PQ. But back to the 1-1 type, it does have a geometrical interpretation. And here it is. 1-1 tensor T can take a vector V, which is some combination in the E frame with V components. Need another Greek index. We'll use beta again. Oh, but we used beta before. Let's see. Mu. We'll go back to, how about sigma? We'll use sigma. That's a different one, because T will have mu and beta. And so I'll be more explicit with what V is. So we should use a lower sigma here, and that's V is the sum. That's an equals. Okay. Well, just like these dual vectors epsilon were linear functions on the E's, we can let T act linearly on V and split across the sums, and these V's factor out. So we can look at a single component of this sum. Let's say the V0 part. Well, the V0 factors out, and we really just have it acting on E0. Now what is this? If we can describe what t e0 is, we can do it for t e1, e2, and e3, and extract what our overall object is. And you'll see the pattern. If you define something in a basis and you define a transformation in a basis, you define the entire thing. So all we have to do is explain how a 1-1 tensor acts on a basis vector. Well, a 1-1 tensor, if you remember, is a combination, and we used lower beta, upper mu, acting on E, and in this case, the ordering of E and epsilons won't matter. It will in the future. E, it's a lower mu, and an upper beta acts on E0, except this is a sum over mu and beta, and we actually have linearity in the other direction. For the same kind of reason, we have linearity of matrices, where either matrices can act on a sum of vectors, or a sum of matrices can act on a vector, and you just apply each matrix separately and then add the result. So we actually get another level of linearity. So V0 is still out in the front, but now we have this. We can act on E0 with each of the basic 1-1 tensors, E, mu, and that should be an epsilon. Epsilon beta. Put another bracket here. So this thing acts on E0, and the result is enclosed in the square brackets, and we sum over the results. Okay. Well, we know that these eat these and give a number, so we can just take that number and multiply it by the E mu, which is somewhat in line with this tensor product being multiplicative. So if we just define that thing to be the same as E beta acting on E0, scale that with the t components, that should not be a mu. That should be 0, and V0 is out here, and we still have our sum. Well, this simplifies somewhat. If we let our 0 index be just our sigma index, and let it be more general again, so we can condense all of these computations into a single computation, and remember this is over beta and mu. Well, we just have our old friend again, the identity matrix. So this is now a sigma, this is still a beta, this is a sigma. If we go back to the beginning, we had this sum over sigma, which defined V. So now we do it for all components. We'll bring back that sum. We can move the sigma sum all the way inside. And all that does is replace the index sigma with the index beta, because delta is the identity matrix. So the sigma sum disappears. So V is replaced. We have beta, E beta. This is somewhat similar to the base transformation law, except now the components and bases have the same index, and they don't seem to transform oppositely. Really what this is a linear transformation, where instead of preserving an overall object V, we are just getting a new one, which we can call TV. And TV is the resulting vector where when we act by these T components and perform this sum, we get something new. So let's look at a particular value of a TV beta. So maybe it has an E0 component. We're working in a fixed basis this time. That's the other difference. If we look at E0, we can project to E0 and see what we get. Well, we have an E0 part where beta is 0, but we still have this sum over mu. So if T 0, 0, and I think this is wrong, so I'll leave it here.